Okay, this is a file that's solving the two-link plunger using vector loops. Again, I'd like to quit everything just in case I've been using Mathematica before. These statements right here come from that vector program that you can download. It's just defining the I, J, and K components. And then I like to begin vector loop problems by defining a simple way of typing in the values that change. Notice that in Mathematica you tell it that something changes by saying that you do a square bracket t, meaning that theta is a function of time. So I'm defining cosine and sine as cosine and sine of this variable. And then I've got this x defined as ex, and I note that to Mathematica that it is also a function of time, so I'll execute that one. And then here's my loop equation, so it's fairly simple. I'm using fractions rather than 0.3 because it'll then use fractions, and oftentimes, not always, but oftentimes, Mathematica will give you prettier looking results if you allow it to use fractions. So anyway, that's what I'm doing. So no big deal, but you could, anyway. So here's the loop equation from the PDF file that I've done. Yeah, I think that makes sense, right? So you execute this, and notice that it puts in the theta and the x as being functions. Also notice that it has a the loop equation. One of them is already simplified. Realizes that the j component is 0 equals 0. Anyway. So what you can then do is take a derivative of that. So you take a derivative, and we'll call that the d loop, and that's a derivative. This is how you take the second derivative, and it does it fairly easily. And now all I'm going to do is I'm going to solve this thing. So I'm going to first of all solve my loop equation, and the only variable in the loop equation, if you notice right up here, the only variables are I guess I should have solved for, yeah, okay. There's either x or there's theta, so I probably would want to solve for theta. Let me just make that change real quick. Like, so you say, we'll call it ANS2 second, oops, let me see if I can type it right, ANS2 equals solve the loop equation for theta of t. And so when you're solving for the angle, there's an infinite number of them, so it's saying here is the solution, right? It's either positive angle or negative angle, because it doesn't know which one is which. All right, so you probably want the positive angle, so it's the inverse cosine of 5x divided by 3. And then this thing right here, if you notice, it's 2 pi, that's 360 degrees, and it's saying that C1 is any integer number, so it's 0, 1, 2, 3. So in other words, this is the answer, plus 360 plus 360 times 2 plus 360 times 3 plus, and I think you get the idea. So Mathematica doesn't know that all you want is the first one, so it gives you all of them. But anyway, no big deal. Okay, so now what I'm doing is putting in the value of x, and I'm solving the derivative equation for theta dot. So you execute that, you end up with a theta dot equals this right here. And then again, just like before, x dot is equal to v. So I say x dot is equal to v, and say give me the answer now if x dot is v. And so there you go. That's the same solution that you got for using special points. And then you need the theta dot. So for example, if you look in the acceleration equation, this one here, look in that equation, the variables that are unknown in there is x double dot, theta double dot, all in here. Now you never solve a second derivative equation for first derivative. So the only double dot terms that are in here is theta double dot, theta tick tick, and the x tick tick. So those two variables are the only things that the acceleration equation is used for. Anyway, so what you do is you solve the second derivative for the second derivative equation for the double dot terms. So if you solve that, you end up with the theta double dot as this value here, and notice that it is in terms of the x double dot. And so just like before, x double dot is a negative a, and then you just simply say, tell me what the value is for the answer, and theta double dot equals this stuff right here. And if you notice, that is the same thing as it was when you solved for the special point equations.